thank you so much for coming to the Fairness in Algorithms. What were the set of words we used for the title Fairness? Algorithmic Fairness tutorial. I'm Jamie Morgenstern. I'm a professor at Georgia Tech. And I'll let my two co-presenters introduce themselves.
Hi, I'm Sharad Goel at Stanford.
Hi everyone, I'm Cummings, and I'm also faculty at Georgia Tech. And so roughly the format that we're going to use today is that Sharad's going to talk for the first half, roughly 90 minutes plus minus. Then we'll have a break. You guys can get some more caffeine so you can be ready for Rachel and my presentation after that. I think the thought is that at least we're expecting some amount of discussion. So we'd rather it be a discussion than buzzing through slides. So, okay.
Okay. So I'm going to try to get through an unwise amount of material, I think, in 90 minutes. But please slow me down if you have questions. I'm happy to address them. Can everyone hear me, or is it a little bit? Can you hear me? Okay. And I should mention that this is all joint presentation with Sam Corbett-Davies, one of my PhD students at Stanford, who unfortunately couldn't make it because he was graduating yesterday. So bad timing. We didn't check our calendars before doing this, but he's here in spirit. Okay, so the idea is to understand fairness in algorithmic decisions, but I think a useful way to understand algorithmic decisions is to talk about fairness in human decisions. And so this is the first part of that talk. And once we understand that takes us about 90% of the way there to understand fairness in algorithmic decisions. So this is the rough format of the talk. And to understand discrimination in human decisions, I want to first talk a little bit about common legal and social understandings of discrimination. So in the law, there are two common formulations of discrimination. The first is what's called disparate treatment, and the second is what's called disparate impact. So disparate treatment, it gains its force from the Equal Protection Clause of the 14th Amendment, ratified after the Civil War. So this was really, the idea was to prohibit explicit discrimination based on animus, particularly racial animus, but also gender animus. And the second idea of discrimination is disparate impact, and this is a much more recent concept. And here it detaches itself from intent, like disparate treatment, which is all about intent. This is now about whether or not a decision maker is taking an action, regardless of malice, but for no particularly good reason that has a disparate burden on particular groups. Again, think race and gender. So this gains force from various federal statutes, the Civil Rights Act of 1964, the Fair Housing Act of 1968, various state statutes, for example, California, sadly not New York. But these are the two main types of discrimination that I'll be talking about. And really, because we're in the algorithmic setting and in the statistical setting, intent is very hard to establish. So we're really going to be talking about this idea of unjustified disparate impact. Now, unjustified disparate impact is very closely related to two concepts of discrimination in economics. The first being taste-based discrimination. So this is an idea that Gary Becker introduced back in the 50s. And here, it again doesn't have to do with intent, but it's if a decision maker is acting as if they have a preference to discriminate. Again, they're acting in a way that suggests that their revealed behavior is as if they have this intent to discriminate, although the concept itself doesn't require intent. Now, this is in contrast to statistical discrimination, where here an individual decision maker might make inferences based on group membership, for example, gender or race, in order to maximize profit. But again, here the idea is not to discriminate in any way that's due to malice, but to make money. Money I'm using as a proxy for all forms of utility. So here, think of something like insurance rates. So insurance rates for men might be lower than insurance rates for men might be higher than insurance rates for women. Because of a statistical inference that conditional on age and driving history, women are less likely to get into accidents than men. So that's a form of statistical discrimination where the decision maker is maximizing, is trying to maximize their profit. So in contrast to taste-based discrimination. So we'll really be talking about taste-based discrimination and its analog in the legal setting of unjustified disparate impact. Okay, So now let's dig into taste-based discrimination just a little bit more to get our bearing. So here, again, the idea is that the decision maker is sacrificing utility. They're acting suboptimally relative to some profit-maximizing agent. And they're doing this to satisfy a preference or an apparent preference to discriminate. So one example here is we can imagine an employer who's willing to hire a less qualified man or over a more qualified woman. And this is suboptimal because they're losing money. They're sacrificing utility because they have this preference for this gender bias, this preference for men, and they're willing to lose money to satisfy that preference. So this is a canonical example of taste-based discrimination. So the optimal decision to make in this least stylized setting is that we apply the exact same standard to all individuals regardless of gender, conditional on qualification. We just hire everyone above some threshold, or equivalently, we hire the top K most qualified people. So this is where our statistical tests for discrimination come in. So the idea behind most of these statistical tests is that we're trying to identify whether or not this equal threshold was in fact applied across groups. And so the idea is to test directly for this taste-based discrimination or for this unjustified disparate impact, switching between these legal and economic terms for very similar concepts. Good, so is everyone figured out? Just laying out the foundation for what exactly it is that we're going to be testing for. So now let's switch to a slightly different example to build out some of these ideas. So here it's police searches of vehicles. So by law, police need what's called probable cause to search a vehicle for contraband. And the question of discrimination here is, do officers apply the same standard of probable cause equally to drivers of all races? Again, if they don't, if they, for example, apply a lower standard of searching someone who's black than someone who's white, that is a form of taste-based discrimination. Why? Because for the same amount of effort, if they had applied an equal threshold, they could have recovered more contraband. So again, this is sacrificing utility. It's sacrificing profit to satisfy some apparent need to discriminate or some apparent preference to discriminate based on race. Okay, so now what is a simple test for discrimination in this context? So again, our idea is it the case that officers are applying two standards, one for white drivers and another for black drivers? A very, very simple test for discrimination is we can look at whether or not white and black drivers are searched at similar rates. And a higher search rate for black drivers might indicate there was a lower and hence discriminatory threshold for searching black drivers, right? Now what's wrong with this test?
Correlation, causality.
What was that?
Correlation, causality.
So in a way, maybe do you want to elaborate on this?
I mean, I don't know if just that fact in itself is enough to prove discrimination.
So one thing to clarify is that intent, again, is not a question here in this form, in this way of thinking. Intent is very difficult to establish in statistical tests of discrimination. So it's not a question.
Justification, right? The word unjustified.
Yeah. So here we're using unjustified. So it's very difficult to even talk about what is a causal effect of race on a decision. I won't get into the kind of long history of trying to make sense of that question, but it's a very difficult question to formalize. But I would say really one of the big issues with this type of statistical test, and this is a very well-known issue, is that without more information, it might simply be that there is no discrimination, that black and white drivers were being held to the exact same standard, but for a variety of reasons, more black drivers might be above that threshold. Right? Possibly black drivers might be carrying more contraband, or more directly to this type of test, they might be behaving in a way that suggests that they're carrying more contraband, because that's what the officer observes. So in theory, this type of test, that one race group is being searched more often than another race group, is not particularly strong evidence of discrimination because we don't know the base rates. Now, a more complicated version of this is a regression. So here we really just think of it as a regression with no features. It's just an intercept term for race groups. We can say, well, let's condition on a variety of different factors. For example, does somebody have, are they behaving erratically? Are they, what type of car are they driving? All these other factors that might be indicative of carrying contraband. Now the problem is it's very difficult to collect that type of data. And in these types of face-to-face encounters, one more or less has to accept the fact that we won't be able to condition on everything that an officer might be using in making these types of decisions. So this is a very hard type of test to make to get much traction out of. It's a common test to start with, but it's pretty hard to make particularly strong claims based on this type of analysis. So enter the outcome test. So this is a very clever test. It was proposed by Becker. And it's a very simple idea. So here the idea is, let's not look at search rates, let's look at search outcomes. So what does a search outcome mean? It says conditional on being searched, what are the odds of finding contraband on drivers conditioned on race? So if you're a black driver, what are the odds, and you're searched, what are the odds of finding contraband? If you're a white driver and you're searched, what are the odds of finding contraband? So let me give you an extreme example. So let's say that when I search black drivers, I find contraband 10% of the time, but when I search white drivers, I find contraband 90% of the time. What does that suggest? It suggests that I have a double standard, that I'm willing to search white drivers on the basis of relatively little evidence. I'm willing to search black drivers on the basis of relatively little evidence. It's 10% chance of finding something. And I'm willing to search white drivers only when I'm extremely confident that I'm going to find contraband. So this is evidence of a double standard. Yes?
But if it just happened like in the population, I'll just use different colors. It's like the blue drivers had contraband 5% of the time, and the red drivers had contraband 6% of the time. Then you should, and you don't have any other signals to go on, then you should only pull over red drivers.
So, I would say that's an extreme example. In reality, we have lots of information. And so it's not simply, so if you literally had to make the decision based on one factor, the race of the driver, sure, you might do something like that. In reality, we have lots and lots of information that officers have access to. And so the idea is, based on all this information, is it the case that drivers are being searched in a lower standard based on race?
So I guess this might happen even when the officer doesn't even see the race of the driver.
Yes, exactly.
For other reasons.
Exactly.
In which case it's presumably not discriminated or...
No, so again, I want to be very careful here. So first I'm going to talk about in a minute how this is actually not an appropriate, or this is a problematic test. So I'm just setting this up. It's a very common, I think it is a clever test. It's in fact a test that I recommend to police agencies when I'm working with them as a crude estimate of what's going on, but I'm going to illustrate the problems with this test in a minute. And also to address Vincent's point, that the idea that this is because of race. I'm trying to step away from that. This is the idea that there's no intent necessarily in these types of decisions. We're just saying, are the actors behaving in a way that suggests there is as if they had a preference for discrimination, not that they actually have a preference or they're acting because of race, whatever that means. Yes?
When you're doing these tests, does the data that you have also have these indicators or other things that the officers are looking for when they are making their decisions?
A very limited set, and so that's the idea. That's like the whole beauty of this type of test, is that for a benchmark test, if you want to run a regression, you have to have a whole slew of features to have any kind of reasonable chance of accounting for factors that might be driving the result. In this test, at least in this very simple intuition that I just gave you, and again, I'm going to show why that's not quite the right intuition, but in this simple example of 90% chance of finding contraband on white drivers who are searched, 10% chance of finding contraband on black drivers who are searched, it feels as if there's a double standard, regardless of what other information is recorded in the data. That's not quite right, but I would say it's actually a pretty good intuition. I would say it's honestly the strongest, simplest test of discrimination that I know of.
So to just expand on that a little bit, suppose there's one kind of vehicle that's sort of excellent for transporting contraband, but drivers of one group, for some reason, for cultural reasons, like to also drive this kind of vehicle, and the other group, they don't unless they actually, right? So, so now it's possible that maybe the police say, okay, let's pull over every single one of those cars. And so very often they find like, oh, it's just somebody from this group who like to drive it. So then it's maybe not. So there's a question of what do we mean by discrimination?
So this is what
this or not, right?
So this is exactly why I wanted to lay out our legal and economic framing at the beginning. What we really mean is two different standards. Now, we can argue, well, these are correlated, all these things are correlated with race, and maybe that makes us uncomfortable. As we'll see later, that's a hard argument to take further. Everything is correlated with race, and everything has a disparate impact. The question is it unjustified? And if you are a rational actor seeking to maximize profit, as we're assuming in this type of setup, we're really talking about applying a single standard. So based on all the available information to you, are you making a reasonable choice? So maybe I can move on for a little bit now and see if I can answer these questions. So now here's the main object that's going to really set up everything else that I'm going to talk about. in the rest of this presentation, the risk distribution. So what is this? This is, for every driver, we imagine an officer sees them, and they assign some probability of finding contraband on them. We assume that they're good Bayesians. They take all the information available to them. They fit this logistic regression in their head. They do all this stuff, and they come out with some estimate. And as you'll see, this is not such a crazy idea once we go to the algorithmic setting. It's a little bit, you have to suspend disbelief a little bit in this example, but this is exactly what algorithms are doing, so that we'll see in a minute. And so we just have these point estimates for every driver. And now, over our population of drivers, we have a distribution. Okay, so officer pulls over John, he's going with his family, and it's like 7 o'clock at night, he just came over for dinner, like, okay, low chance of finding contraband. Now they pull over Jamie, she's, it's 2 a.m., her eyes are bloodshot, she's wearing her Baked in Ithaca t-shirt, and have you seen these t-shirts? I just saw them, they're great. It's, now all of a sudden the officer thinks, okay, 50% chance of finding contraband. Now these are just out there, this is not something that's really up to the officer, we're just kind of assuming that that an objective officer just has this information, and all we're doing is recording this information. Okay, now again, this is a bit of a stylized example. It's not so crazy once we get to algorithmic decisions, but to build intuition, let's think of it this way. And now this is our distribution of risk across that population. Good? Okay, so everyone, this is the main object. If you're confused about this object, please ask questions. Yeah?
So are you conditioning this on what set of features is this population referring to?
So the population is just set. We're just in this example, an officer is stationed at some particular place. They stop some set of people, and now let's just say they're stopping everyone who's above a certain speed limit or above the speed limit, and now they're just like doing this type of inference.
So this is that likelihood, not conditioned on anything besides going above.
Yeah. Okay. So we just have this, and again, when we talk about algorithms, the population itself will be much clearer what this thing is. Now, this is for one group, the blue group. Now let's take another group, the red group. Now the risk distribution of the red group in general will be different than the risk distribution of the blue group. And it can be different in two important ways. The first is that the means could be shifted. And so here we're just shifting these distributions over a bit. And now another way in which it can be different is that the means could be identical, but the variance could be different. In this particular case, the red group has a lower variance than the blue group. And what the implication of that is that it's harder to find out who has contraband in the red group relative to the blue group. Okay? And again, this is more or less in this setup, there's no choice involved here. This is just given to us by nature. That we have this population, once we define this population, once we define the attributes that we're willing to consider, we just have these distributions given to us by nature, and now we have to make decisions based on these distributions. Okay, as again, I'll say it's a little bit of a stretch in this particular example, but it's very much in line with when we talk about algorithmic decisions in a few minutes. Okay, so now let's dig into this example just a little bit more. So here we have the same base rate, 30%. This is the example that we're going to consider in these two different groups. And now let's say that the police search in this non-discriminatory fashion, one that's optimized to find contraband. Namely, they're going to search if there's at least a 50% chance of finding contraband. So they apply the same standard to all groups. It's by our definition of taste-based discrimination. It's not a discriminatory policy. And now let's see what happens when we use this type of policy. Okay, so the outcome test, if we look at the hit rate, so what is this? The likelihood of finding contraband, conditional on being searched. That's the mean, the conditional mean above the threshold. For the blue group, it's 60%. And for the red group, it's 55%. And why is that? It's because the blue group has more obviously guilty people. I'm using this word guilty. It's a little bit of a stretch here, but I'm going to use it as a shorthand of people who have contraband on them. So we have, because the tails of these distributions are different, and in general, the distributions will be different, and so the tails of the distribution will also be different. Even if we apply the exact same standard, which by our kind of legal and economic notions of discrimination means that there is no discrimination here. This is a perfectly profit-maximizing, non-biased strategy. Our outcome test is going to suggest discrimination against the red group, incorrectly suggest discrimination against the red group. Okay?
I'm
Yeah.
a little bit confused. So the thing I'm confused about is that you put up these plots which were describing the entire population. You didn't mention any observables or any features that you were using. And then somehow you managed to put a line at 55%, which somehow says that there's some observables that allow you to put the line at 55%.
Yeah. So the idea is that there's two concepts of observable. There's a researcher observable and there's decision-making observable. So the researcher, since we're acting as a third party trying to audit these decisions, we're assuming that we don't get to see the information. The decision maker gets to see a variety of information. The officer gets to see if your eyes are bloodshot. The officer gets to see what type of vehicle you're driving. The officer gets to see the time of day. And because if the officer is incorporating all this information, it ends up with some point estimate. And so now this distribution is not observable to the researcher. Nothing here is actually observable to the researcher other than these two numbers, 55% and 60%.
Yeah, but you're trying to explain what happened, and you've got a picture which I don't think corresponds with. I'm just confused as to what it corresponds to.
So the idea is everything on this slide, nothing on this slide is.
Is the x-axis observed?
What was that?
Is the x-axis?
Nothing is observed here to the researcher other than these two numbers.
What's observed by the police officer?
Everything else that allows them to create these distributions. So again, think of the officer pulls over John, the officer pulls over Jamie, and it says, okay, 10% chance of having contraband, 50% chance.
You're suggesting that they're making this decision based on this 55% mark, which means that you have to have that in the observable data.
They're making the decision based on the 50% mark. This is my search threshold.
And so they decide to search everyone who they believe has probability more than half.
Exactly.
So
Right.
Jason, here's a simple example. Suppose there's a perfect linear model that describes the set of things that a police officer sees and how those correspond to the probability someone has contraband. The police officer applies that linear model to the set of features they observe, and if the number is more than 0.5, they pull the person over, otherwise not. They can implement that. We wouldn't necessarily observe all the features they made their decision as a function of.
Exactly. That's exactly right. And this is the cleverness of the outcome test relative to the benchmark test. Because the benchmark test requires a researcher to have access to the information that the decision maker has access to. Becker's insight was that that information, although it's always available to the decision maker, doesn't have to be available to the auditor, to the researcher, to understand whether or not a double standard is being applied. Now, the problem with this, as this example shows, is that in fact, while this intuition is relatively strong, in fact, it doesn't hold precisely, in the sense that in this example, a single standard was applied to drivers regardless of race, so there is no discrimination by definition, but yet the outcome tests suggest that there is discrimination. And the issue is this problem with the distribution of the risk that the officer is inferring. Yeah, Arvin?
Going back to something you said slightly earlier, when you say the distribution is given to us by nature, are you saying that the officer observables are also treated as, certainly for this problem, but more generally? And the reason I'm asking is one of the main interventions one could suggest is go and collect more data.
Yeah, so I want to get back exactly to that issue, which is quite relevant in the algorithmic setting. So here, I will, my standard disclaimer is the types of issues that we're talking about here require a little bit of a stretch to believe here. In the algorithmic setting, it's much more concrete, and all these choices will become explicit. And we'll see, in fact, that collecting more data doesn't get us out of this problem. Okay? But here, just kind of ask you to suspend your disbelief for just a few minutes until we get to the algorithmic setting, in which case all of these ideas are much more concrete. Okay? Okay. So now let's look at one more problem. It's basically the same problem, but it's showing that that this first problem is when there's no discrimination, the outcome test can in theory suggest discrimination. Here's the reverse, that when there is discrimination, the outcome test can suggest that there's no discrimination. So here, the blue group is being subjected to a lower standard than the red group. So there's taste-based discrimination. Blue drivers in this region would not have been searched if they had been red, and importantly, the police are acting suboptimally to satisfy this preference for discrimination against the blue group. Okay, now what's going on with the hit rates in this example? So conditional on being searched, because of this heavier tail in the blue group, even though we have this lower standard even though we have discrimination against a blue group, the hit rates are identical. So this suggests that when there is discrimination, it's at least possible in theory for the outcome test to suggest that there is no discrimination. Yes, please.
So the way that your distribution is representing uncertainty, whatever model they are using for the prediction of likelihood. So if you take into account that uncertainty and set a lower threshold for the group for which you have more uncertainty, and is that discrimination?
So right now, I'm assuming, so this is something that Jamie and Rachel are going to talk about, and I'll make this assumption clear in a minute. We're really talking about, we're assuming that we just have the probability. Even talking about second order probabilities gets a little bit more complicated, but here just think that officers in the mind are fitting logistic regression with lots and lots of data. And so we're not worrying about the second order issues. If we don't have a reasonable theory that helps us understand what's going on in this case where we have lots of data, we don't even have a chance of understanding what's going on in these more complicated cases.
Like, are they saying this distribution itself, what does it mean? Otherwise, if there is no uncertainty, there is no distribution.
Oh, yes. So there is. So this distribution is deterministic, is a distribution over deterministic probabilities. And so why is that? So the distribution is just, let's say it's people in this room. I can ask, what is the probability that any one of you has contraband on you right now? Right, you either do or you don't, but I have some model, and I could say I'm going to use all this information available to me, and I'm going to say, okay, 1%, 2%, 10%, and now that implies a distribution over this population of probabilities. So there's no uncertainty. This is given to us, this is a distribution of probabilities over a fixed population, and so it is a meta distribution. So it's a little bit of a complicated object, but it's important to understand that this itself doesn't have uncertainty.
And one thing that I'll emphasize more in the second part is that we're not thinking about necessarily learning a parametric model here. I think the assumption is that we have lots of data of each particular set of observables. So we don't have some model which doesn't have the correct probability of y given x for any x, right?
And I'll make that assumption clear in just 2 minutes. So I think that's
where some of this is coming from. Yeah.
Okay, so now just to summarize what has happened here is this is what's called the problem of inframarginality. So this is an idea from economics that actually hasn't gotten a lot of pickup, even though I think it's an incredibly powerful idea. And this is really the answer to all of the issues that we're going to discuss for the next hour. So what is this idea of inframarginality? It means that when you're trying to estimate discrimination, you care about the marginal decision. You care about where is that threshold? Where are you ambivalent between searching or not searching? Something like hit rate is an inframarginal statistic in that it averages over the distribution itself, or at least part of the distribution. So it's averaging over a part of the distribution which lies away from the margin. Now when you do that, as these examples has shown, then in fact those inframarginal statistics can be a poor proxy for what's happening at the margin. And the implication is that inframarginal statistics like hit rates are a poor proxy for discrimination. Now, just to show you that this is actually a real problem, it's not a theoretical problem, it's a real problem that we've encountered. So let me give you one example. This is in Raleigh, North Carolina. We looked at police searches there, and we find a hit rate for black drivers of 16%, so conditional on being searched. What is the likelihood of finding contraband? For white drivers, we find a hit rate of 13%, conditional on being searched. White drivers are found contraband less often than black drivers. The outcome test would suggest discrimination against white drivers. It would suggest a lower standard is being applied to white drivers relative to black drivers, which would be indicative of taste-based discrimination. The problem is that this isn't really what's going on in Raleigh, or this is what we don't actually think this is what's going on in Raleigh. And so why not? Well, black drivers, as it happens, in the data in Raleigh are pretty good. And so what we see is that black drivers, for whatever reason, tend to have more plain view contraband. So they carry drug paraphernalia and other indicators of contraband in plain view of officers 3 times more often than white drivers. Because of this, there's a population of black drivers that are very likely to in fact have contraband. That's exactly the type of situation that we saw earlier in those stylized examples. And if we try to infer these distributions of risk, this is what we get. I won't go into the details of how we infer these distributions of risk. I'll just point you to this paper that we have, Sima et al. But this is what we find when we apply that test to the data, that the black line, these are black drivers, have this heavier tail. But in fact, we infer that the search threshold is lower for black drivers relative to white drivers. And so this suggests taste-based discrimination against black drivers, but the hit rate, sorry about that, the hit rates for black drivers is higher than the hit rate for, white drivers for black drivers is higher than the hit rate for white drivers. So again, does this make, so this is a very subtle problem that we have to distinguish between the hit rate, because the heavier tail of black drivers, even if we have a lower threshold, which is our definition of discrimination, the hit rate for black drivers is higher than the hit rate for white drivers. Okay, so we don't think this is just kind of an artifact.
So are the axes different than on the previous slide? Because I thought on the previous slide the y-axis was kind of likelihood of carrying contraband, and the x-axis was kind of some like test statistic that they formed out.
No, this is still the density. So it's the density in both cases. There I kind of draw on this like nice density. This is a little bit of a more realistic density where you have.
So what's the y-axis then?
This is the density. So it's like kind of so if you integrate it, it would go to 1. But it's so this is all that's being shown. Okay, so the intuition I think is clearer when you have these nice normal looking things. In reality, the vast majority of drivers are very low likely to have contraband, so you have these types of distributions. Okay, but they're showing the exact same thing. This is based on empirical data. The other was purely stylized. Okay, so now,
Question.
yes.
You could totally tell me to like jump to the coffee break.
Yes.
But I'm curious how the data was come upon that suggests that the contraband in plain view is like 3 times more likely to be. I'm curious like whether they did a random stop of like 1 million drivers and like look to see if there was, or if that's conditioned on.
Oh, so this was very easy. In fact, one of the justifications for establishing probable cause is plain view or plain smell, and that's indicated on the stop form. So we know, in fact, that the officer is indicating that there's.
So that's conditioned on being stopped by the police.
Yes, exactly.
Okay.
And that's all these decisions. Our population is the population of stop drivers.
Okay, and they were stopped for a variety of
Yeah,
reasons.
and also I'm not saying that this is talking about discrimination only at a certain decision point. We're not talking about discrimination previous to that decision point or after that decision point. We're talking about discrimination at this one decision point. Yes?
I don't understand why you aren't doing these tests conditioned on what the officers report on the form that was their cause for doing this search.
Yeah. So the idea is that this would run into the problem of omitted variables. So this is the issue of the benchmark test. That if I say that, okay, well, I'm going to record a handful of features, and I say conditional on those features, black drivers are searched more often than white. But what is the obvious problem with this? It's saying, well, there's lots of other things that are not recorded on the form. And so this is omitted variables. I would say conditional on car type, conditional on even plain view contraband, conditional on all these other things. Let's say one group is searched more than others, I might quite reasonably suspect that that's because of behavioral attributes. And so it's very, very hard to get around omitted variable bias in these types of face-to-face interactions.
I guess I would have assumed that the officers have to give the reason for their probable cause.
So I would say, so they have to justify it by some means, but they don't. I would say they do, and they even write narratives.
So just use that one variable.
Which is the one variable?
The one variable they write on the form was their justification for probable cause.
But the behavior, what they write in the form, again, think this is the real world. What are they going to say? Well, they're acting erratically. Are they acting erratically as a 5 on a scale from 1 to 10? Or are they acting erratically as a 7 on a scale from 1 to 10? Is it a 7.5 or is it a 7.1? Is it that their eyes are pink or are their eyes a slightly darker color? It's like omitted variable bias is very, very hard to get around in face-to-face interactions.
Especially if they were going to be like measured with expect something about the probability that they were doing a good job on different types of stuff.
So this is really the key insight of Becker, is because of many variable bias, it's so hard to get around, let's condition let's not look at the rate of action, but the rate of success. So now let me just move us forward. I think a lot of these issues will be a bit cleaner when we get to the algorithmic point. We're really gonna, in some ways the talk is already done. Now everything else is a corollary. But we're gonna talk about this in 5 different ways to hammer home these points. So now, what is the connection to ML predictions? And this is our way into algorithmic decisions, is we can think of the hit rate as the precision of a human decision maker. What does this mean? This means that conditional on a positive classification, so conditional on searching, thinking someone has contraband, how many actually do have contraband? So this is exactly the analog of precision in an ML context to the human decision-making context. And the TLDR on this part of the talk is that the precision is a poor indicator of discrimination in this taste-based sense, which again maps quite nicely onto our economic and legal understandings of discrimination. So this inframarginal precision statistic is a poor proxy of the threshold itself. Okay, so now with this framing, with this background, Vince, you want to?
I just wanted to make one more point. So we seem to have settled on this definition of discrimination as applying different thresholds to different groups of people. But I wonder if that's even enough, right? Because if we imagine now race is the only observable feature, and it so happens that 16% of black drivers carry contraband and 13% of white drivers, and we decide to set our threshold at 15%. Right, and so you say, okay, well, it's the same threshold for everybody. We search everybody who's black and nobody who's white. Yeah. But that puts a huge burden on the black population. It has its own problems.
So now one can ask whether or not it's justified. So I'd say so first of all, it's complicated. And one thing I want to say is that both the law and the economics literature have developed with a sense of practicality in mind. Remember, this idea of taste-based discrimination is really motivated by an intent to discover, is somebody doing something that's bad? Now we can come up with examples where the only thing we observe is race, and now all sorts of things are going to go haywire. This is really not the spirit of, I would say, either this particular talk or a lot of this literature, is that we're not trying to break things we're not going to try to push these things to their theoretical limits, because in fact, many of these ideas break. But I would say the intuition is relatively strong that if you're applying different thresholds, something is funny, and if you're applying the same threshold, at least you've passed this kind of first bar of reasonableness. But certainly this isn't the end-all of discrimination. I'm going to get back to some of this at the end. So maybe I should.
And I will say, Vince, there are cases in practice where you do want different thresholds, and that's sort of not the cases that he's talking about in this talk, but for example, if you wanted to admit students to your schools, and you want to recognize race is correlated with socioeconomic status, which is correlated with test scores, and so maybe I don't want to apply a single threshold on a person's SAT scores. Maybe I want to recalibrate for a race. And so there are other fairness notions that are used in different contexts that do purposely choose different thresholds across.
And I'll try to argue that in fact many of these examples can be incorporated into this framing. And so I would say that this idea of discrimination covers many, many cases. Nearly every paper that's been written recently can be framed this way, although not all, which is what Jamie and Rachel are going to be talking about. But many papers can be formulated in this way of acting efficiently. Okay, so now let's move on to algorithmic risk assessments. So many decisions are based on making these risk assessments, at least in theory, and then acting on that information. So the example of officer searching is one, lending is another one of these examples, pretrial detention is yet another example where judges decide whether or not to detain a defendant or release them prior to trial. So they're making these assessments, these statistical assessments of risk. They're using this information to make a decision afterwards. And in many of these contexts, what we've seen is that statistical risk assessments are often better than human risk assessments. Although in theory, these are the same thing. In theory, we're just starting with risk assessments, and we're making decisions based on that. So it's the exact same setup, but the shift from human to algorithmic decision making is coming in this first step of saying, how do we get those risk assessments in the first place. And statistical risk assessments have shown to be better, perhaps unsurprisingly, in many of these contexts than kind of intuition alone. Okay.
Although in some cases not.
Not in all cases. So these are often cases where you have lots of data, where rich set of data points and also a rich set of features. And this is kind of a decades-long literature that goes back to psychology. So let's look at pretrial detention. This is the example that I'm going to use moving forward, is that judges have to decide after arrest whom to detain and whom to release awaiting trial. And again, this binary distinction is a little bit of a stylized version, although it's not. Actually, in some states, it's more or less the exact choice that judges have to make. And this is a high-stakes decision. Why is that? Because a judge has to balance the social and financial costs of detention with the benefits of reducing pretrial crime. So again, they're trying to assess the likelihood of recidivism. Based on that likelihood, they're trying to make an assessment of what action to take. Now, a couple of years ago, ProPublica, this investigative news organization, they had this pretty explosive article come out called Machine Bias. Their software used across the country to predict future criminals and its bias against blacks. And that's a claim that I want to evaluate for the rest of this talk. So can we make sense of this claim? Is this, as stated, accurate by conventional legal and social ideas of fairness? The summary is no. That I'll try to argue that, in fact, it's very hard to justify this type of assertion, but the reason itself is relatively subtle. And it comes to all these issues that we've been talking about previously about risk distributions. Okay, so first, just to give a little bit of grounding on this, what is a risk assessment tool? What is it that they're actually talking about, the judges are using to make these types of decisions? So here's one example. This is not the example, this is not what was used in Broward County, but it's a pretty common one that is really just a checklist, a weighted checklist. So you have some features, for example, what's the current offense, a violent charge, what is your age, do you have other pending charges at time of the offense, and each of these factors comes with various points. So for example, if you're currently being arrested in a violent offense, you get 2 points, otherwise you get 0. And this is a coarse approximation to one's statistical likelihood of having violent recidivism during the pretrial period. Okay, so this is what's actually used in practice. Now I'm going to step away from this a little bit and go back to the probabilistic world where we don't have these coarsened estimates, but we actually have the real probability estimates based on all the available information. But the idea is quite similar to what is shown here, and this is in fact what's being done in practice. Now, what is it that ProPublica did? They looked at 3,000 white and black defendants who were assigned these COMPAS risk scores in Broward County, and they also determined whether or not these defendants recidivated. So they tracked them for 2 years, 2 years out of incarceration, and tried to determine, did they actually recidivate? Now, this isn't quite what you would actually want to do. What you actually would want to do is say, if I were omniscient, I would say, what would have happened had I released this individual rather than detain them? What they actually did was say, something happened, they were either released or detained. At some point they were released, and now let's look at 2-year period after they were released and just use that to estimate the counterfactual of what would have happened had they been released at that immediate decision point. For what I'm going to talk about, this type of slippage is fine. I'm going to abstract this away and say that we just have this known label y. In practice, it's difficult, but not impossible to generate this known label y. But I'm just going to assume that I have this right now. And I'm also going to assume that there's no measurement error. So I know perfectly what this thing is, what the counterfactual is, and I just get to observe it. Now, this is a strong assumption. And I think it's one that's quite important that Jamie and Rachel are going to touch on. I will note that this is, in fact, the standard assumption in the vast majority of algorithmic fairness papers, and it'll help us get to an understanding of what these types of tests of discrimination mean. Now, the second assumption, which I'm going to make, which is relatively mild, in this case at least, is that I have the true risk distribution. So what that means is that I have the conditional probability of seeing this thing of y equals 1 conditional on the features that I have observed. So why is that if I have lots of data, we can take some non-parametric estimate. We say I'm going to put everyone into these bins. I have lots of data. And so now in any of these bins, I just get to see the frequency. So it's a purely frequentist estimate of the probability. If we have lots of data, we don't worry too much about the form. And so we might do some smoothing with a parametric model. But I'm just going to assume that I have this risk distribution, these individual level risks available to me. OK? Yeah.
So in ProPublica's analysis, they took the 2-year mark to be, can you hear me? In ProPublica's analysis, they took the 2-year mark to measure the outcome variable y, because that's what NorthPoint's marking material and what they're...
Yeah, so that's a pretty standard proxy for this counterfactual outcome. If you take a 2-year recidivism period, I'd say that is supposed to be a proxy for recidivism in the pretrial period itself, normalized over time. So it's, you could take a longer or shorter period. Again, I'm not going to get into the details too much of what that outcome is, other than say that one could take many reasonable proxies for this thing, and that's the one that in practice is used.
So is there another one that you would prefer, that you would recommend instead?
I think it's pretty difficult, and I wouldn't be able to make a strong claim right now about what the preferred outcome is. I don't think it's a crazy measure.
And I'll say that we'll talk in part 2 of this about how to handle things when you don't know the true risk, and both what you can do and some challenges and some open questions.
OK, so now we want to go from features to decisions. So how do we do this? Well, we have some features go in. So again, let's think of this pretrial recidivism. We have this criminal history. We have age. We have all of this other, we have the charge information. We stick it into this box. We get a prediction out of it. That's just more or less given to us by nature, that box. And now we can take that information. We can start making a decision based on that risk and based on any other information that we want, in theory. And now we have to make the decision, detain or not detain. OK, now let's again look at this first box of this prediction. Now this is, again, totally given to us by nature once we choose the features x. So if I say what it is that we're going to condition this probability on, the way I've set up the problem is if we have lots of data, I have the probability conditional on x. This is not up to the algorithm designer. The algorithm designer can choose the set of features, x, and the algorithm designer can also choose what to do with that decision or with that prediction afterwards, but they can't actually change the prediction itself. They can choose to ignore that prediction, but they can't change the prediction. That's just information that's out there once I set x. Now, this gives rise to this distribution of risk. And I want to make 2 points. So the mean of this distribution is fixed for all choices of x. So once I tell you once I tell you what y is, regardless of what x is, the mean of that distribution is just the overall rate of recidivism. So that I can't change. The only thing I can change is the shape of the distribution given my choice of x, because that's going to change my conditional probabilities, which changes my distribution of conditional probabilities. But the mean of that distribution I can't change once I'm willing to accept that y is perfectly measured, which was my assumption at the beginning. OK, so now the optimal decision, which is not hard to see in this framing, is that conditional on risk, all I do is apply a threshold to that risk, and I ignore all other information. So conditional on knowing someone's likelihood of recidivating, I don't need to know anything else. I don't need to have different standards for different people. I'm saying you're 20% likely. It's not that you're 20% likely to recidivate, and I know that you're white or I know that you're black. I know that you're 20% likely, and that's the only information that I need to make this type of decision. So what does that mean? It means that I apply, if I want to behave optimally, I just apply a threshold. Again, we've seen this type of decision making before. I just apply a threshold to this risk distribution. And I say that what does it mean that I'm on the threshold? Let's say my threshold is 50%. That means I'm ambivalent between detaining someone who has a 50% chance of recidivating and not detaining them. So another way of thinking about this is I'm willing to sacrifice 2, let's say, assaults, or I'm willing to detain 2 people for 1 assault. This is the type of trade-off that I'm willing to make. And once I determine, that's kind of independent of the risk distribution, once I determine what my cost function is, where I'm willing to set that threshold, all I have to do is apply it, and I know who I'm going to detain and who I'm not, knowing only the risk distribution. Yeah?
You said optimal, so I was wondering what the objective was. But
So here, I'll come back to this a little bit at the end. Optimal, I would say that the cost is detention.
Right.
So there's a financial and social cost of detention. And then the benefit is public safety, reducing recidivism. And so this is by law what we're trying to optimize for. And I would say this is also, in this particular case, it's relatively, I would say, persuasive to think that these are the immediate, the most salient costs and benefits. Okay, so now, again, this optimal threshold, what does that mean? It's trading off between detention and recidivism in a way that is most efficient. So for the fixed number of detentions, how much recidivism can I prevent? That's what I'm trying to optimize for. And what does taste-based discrimination mean in this setting? It means that I'm willing to set two standards for my different groups. I'm willing to detain white defendants at one threshold and black defendants at another threshold. Why is that taste-based discrimination? Because detaining the same number of people, so here's an example of that. So I have my blue group, I have a lower threshold than my red group. And this is exactly what we thought of as taste-based discrimination in the policing context. Here, in the algorithmic context, it's the exact same thing, that I'm willing to detain these extra blue people in the middle because I have this taste, in this case, for discriminating. Okay, and another way to think of this as losing efficiency is that if I wanted to detain the same number of people, I could set a single threshold, which would be moved up, and I would have less recidivism. So I'm sacrificing my benefit in order to detain more people from the blue group. Good, so it's the exact same setup that we had in policing, but now we're applying it to algorithms in this case of pretrial detention. So now, what does that imply for fairness in this algorithmic setting? I would say that it implies this single threshold view of fairness. I'm going to actually use this word fairness relatively infrequently. I'm using it now because this is the way that we tend to refer to it, but it's not actually a concept that comes up too much in law or in economics. That here the idea is that we're detaining equally risky people, we're treating equally risky people equally regardless of group membership. So I might say that at 50%, I'm going to detain you regardless of whether or not you're white or black. This has the benefit of I don't need to look at group membership conditional on risk. There's no taste-based discrimination in this kind of economic and legal sense. It's in line with these legal and social norms, and in fact, it's exactly what is done in practice.
And this is true even if group membership is one of the features on which.
Yes, and I'll get back to that in a minute, but it's yes. And in fact, I'll argue that it has to be one of the features.
Okay, so it's not, so like regardless of group here is little.
So conditional on risk. Conditional on risk.
So
And I'll say
it could be that group membership is.
And I'll say that that's in fact what you have to do.
And this isn't sort of taking into account that like the decision maker might ultimately have some control over the set of features which are going to be used.
So I'll come back to that, but I'll say that once I fixed my features, and I'm willing to apply this everywhere. And so here I would say you're just using all the information available to you. That in fact this is what you can do, modulo trying to collect more information. And I'll say collecting more information is actually not as straightforward as one might think. Okay, so now this is kind of, I would say this is my positivist definition of fairness in many contexts. I'm using the idea in this one particular example of pretrial detention. I'd argue that applies to many different contexts, in particular in lending, potentially in employment, potentially in these types of police searches. This is I would say, a general concept of fairness in these algorithmic settings. Now, it differs from the popular recent definitions of fairness that have come out of the CS literature. So here, there are three classes of fairness definitions that have recently been proposed: calibration, error rate parity, and anti-classification. So I'm going to go through these one by one, and I'm going to argue that in fact all of these definitions, even though they've been proposed as reasonable definitions of fairness, in fact are highly problematic. The calibration, I'll argue, does not in fact preclude taste-based discrimination, so it's a relatively weak standard that doesn't get us much assurance that we're behaving in a way that we'd be happy with. Error rate parity is even more perverse. It almost always leads to taste-based discrimination. So efforts to satisfy this criterion will almost always be discriminatory by common understandings of law. And now anti-classification, this idea that we shouldn't use protected characteristics, again, can often lead to discrimination. So I'll argue that all three of these definitions, even though they've been posited as reasonable fairness criteria for algorithms, in fact, are highly problematic to apply in those settings. Okay, so let's start with calibration. So what does calibration mean? It means conditional on risk score, groups should offend at equal rates. So here, this is real data. I'm going back to Broward County, and I'm looking at these compass scores at the bottom. So I've switched to the not probabilistic estimates with the actual compass scores that were given to defendants in Broward County. And what do we notice here? That let's say a condition on any one score, let's say a 7, regardless of whether or not you're white or black, you have about a 60% chance of recidivating. And this is true across the entire risk distribution. So what this means is calibration, the definition is conditional on risk scores. Groups should reoffend at equal rate, regardless of race. Okay, it seems like a quite natural criterion to have. In fact, any probability is going to satisfy this definition. So in the beginning, I assumed that there was, I assumed that we have these probabilistic estimates. By definition, it'll satisfy that property. But in fact, it doesn't preclude taste-based discrimination. It's a relatively weak idea of testing for discrimination. So let me give you a stylized example. So here, I have my distribution of defendants. On the x-axis, I have my probabilities. So 0.1, 10% chance of recidivating, all the way to 0.7 on the right. So I have my lineup of individuals, and I just have these probabilistic estimates that these risks associated with every individual. And my decision rule is to detain everyone with a risk score greater than 0.5. Okay, I've decided as a society that I'm willing to detain 2 people for every assault prevented, and now I'm going to apply that to this distribution of defendants. Okay, now how can I create a discriminatory yet calibrated score? What I'm going to do is I'm going to take the individuals on the endpoints, the high-risk people and the low-risk people, and I'm just going to combine them. So I take these people on the endpoints, I combine them, they have a 40% risk on average, and all of a sudden I'm going to say, oh, let's forget about the fact that I know this person is low risk. I'm just going to assign them 40%. Let's forget about the fact that this person has high risk. I'm going to assign them 40%. The reason this is calibrated is I just took all of these people, I lumped them together, and I balanced my high-risk people with my low-risk people, and now I just erased information. So now the scores are still calibrated, but in this case, no blue defendants are detained. So I can imagine behaving in this way to discriminate in favor of the blue group by saying, let's just pretend I have this information for you. We're not going to use this information that I have in my data. I'm just going to not fit my model using that data. That's more or less the same thing as the example that I just showed. And now all of a sudden, I'm saying, oh yeah, everyone looks kind of average, low risk. I don't need to detain anyone. And this is, I would say, a modern version of redlining. It actually goes in the reverse, where in redlining, the historical practice of redlining, we say that we're going to make lending decisions based on neighborhood. We're not actually going to make lending decisions based on individual creditworthiness. So I'm going to ignore all that information that I have about you, and I'm going to make this very coarse prediction based on a handful of features, in redlining, just neighborhood. And I'm going to push everyone to one side of the threshold or the other. Yeah?
Does the multi-calibration get around this a little bit?
I'm sorry.
This multi-calibrated idea, I don't know if you've seen this before, does it get around this a little bit?
Can you explain the idea?
So the idea is to make it, I guess, to calibrate it on a large class of statistics, so that it should be, like, if you can't put people, I guess, to say that it should be calibrated on the race, but also then it should be calibrated on whether or not they had a previous crime before, and it should be calibrated on just a large set of statistics. So it has to be kind of calibrated down the tree a little bit.
So I'd say the positive way of saying that is that these should be the best scores available.
Yeah.
And in theory, if you just give me the scores and no other information, I can't tell if you're using the best scores available. The only way you can do that is if you give me the features. And if I give you the features, then I can say, okay, I'm going to fit my own model, and it looks like, in fact, this is it, and you're not throwing away information that's actually useful. And so I'd say talking about calibration is reversing the question. The higher order concept is we want the best scores available. The if you have the best scores available, by definition, or if you have any probabilistic scores, they will be calibrated. But talking about satisfying a calibration criterion, in fact, misses the point that we really just want the best scores available. And again, anything short of that is potentially discriminatory. Okay, yeah.
I'm just confused because initially, for your definition of fairness, you assume many things are fixed, features are given, etc. And now you're showing that another definition is not robust to.
Yeah, so here I can say, yeah, so here I say x is fixed. As the algorithm designer, I could throw out half of x. But if x is there, then that's what I want to use. So the algorithm designer can say, okay, I just want calibrated scores. You gave me x. I'm going to output something, but it's not actually going to be probability of y given x. It's going to be probability of y given x bar.
So you want to augment calibration to have a
The what?
You are augmenting calibration to
So I would say that I avoid the word calibration because it conflates the estimator with the estimand. The estimator, calibration here, is a check on whether or not you've actually fit a reasonable model. Really what you want to do is fit a reasonable model with all available information. Any of these models will be calibrated, but to talk about calibration is a very, so the other way to think about it is like I can say, well, my risk score should all be between 0 and 1. Okay, that's true, but it actually doesn't tell me much about the actual property that I want these things to have.
But isn't the same thing within the likelihood probabilities that you have to begin with?
That what?
Your model, the likelihood probabilities that you have to begin with, which are calculated based on something, what's the likelihood of a person doing it right? So that also hides some information about like how they were calculated. And
So the point is you in fact can't, if you give me the scores, I can't determine whether or not you fit the best model available. You can tell me, okay, you gave me x, I'm outputting probability of y given x. If I don't actually have access to the outcome, I can't verify that. And this is why I'm pushing back against calibration, because it's a relatively weak check that the decision maker has done something reasonable. And in fact, we see that we can outperform decision makers who have calibrated scores. Yes?
I interpreted what you just said in response to the question as it's a necessary but insufficient condition.
Yeah. Yes, exactly. And
it's necessary.
So even necessary, I would say it's necessary in the same sense that my probability should be between 0 and 1. Strictly speaking, it's true, although it's such a weak criterion that I don't even like to think of it as necessary.
well, but do you have any example where your solution is not satisfying calibration?
Oh, no, it has to satisfy. If it's a probability, it has to satisfy. It's the same way that any risk score has to be between 0 and 1. Now, this is a more rhetorical point. It certainly is necessary, but there's lots of things that are necessary. And in this case, I would say the mental model is not thinking, okay, I want to satisfy calibration. The mental model is, I want to get the best risk model that I can generate. Not say, I've done something, is it calibrated, go home. And this, in fact, is all of applied statistics. Saying that you give me data, I need to fit the best model I can do. I don't check whether or not it's calibrated. I'm going to go through a variety of other ways to ensure that I've done the best that I can do. Maybe that means that I fit a nonlinear model. Maybe this means that I do some sort of regularization. All of these are going to give me calibrated estimates, but I don't stop once I have that. So it is true that it's necessary, but it's, I would encourage people not to think of it as a necessary but insufficient condition. I would think of it, the shift as being, it's a poor proxy of whether or not I fit the best model I could find. But this is a rhetorical point, not a technical point. So this is, you kind of as a applied statistician, I tend to think this way, that I'm trying to, that it's a low bar to satisfy. Yeah.
Is this kind of like a response to the idea of stereotypes might be well calibrated? You don't want to necessarily always ignore stereotypes. Like Asian men are shorter on average, but like we still let Jerry Lin play the NBA.
It's actually different. I would say it's a different point. So this is really how do we determine whether or not my model, so that's a form of statistical discrimination if it's accurate, which for the most part is justified. So it's a slightly different point. It's saying that if you really are trying to fit the best model you can, if you're stopping at calibration, you're probably leaving a lot on the table. So maybe I'll move on just to try to, these issues will come up again, but just get through a little bit more of the material. So now let's look at error rate parity. So what is the definition? So here I'm going to look at false positive rates, which is one particular type of error rate. So what is the false positive rate? This is actually the definition, or this is the concept that ProPublica used. What is the false positive rate? it looks at among the population, the subpopulation of people who would not have reoffended, so y equals 0, how many of them were detained or equivalently were rated high risk. So I'm using this detained or high risk interchangeably, so I'm just for shorthand. So among people who would not have reoffended, how many are rated high risk? Okay, so now this is the error rate, these are the real error rate, the false positive rate disparities in Broward County. 31% of black defendants who did not reoffend were rated high risk. 15% of white defendants who did not reoffend were rated high risk. So the false positive rate is twice as high for blacks than for whites. Again, this was interpreted by many to be quite startling, and maybe I'll just ask, how many people see this and feel viscerally like something has gone wrong with the algorithm? Don't feel bad. This, I think, is like a quite natural response. I'm going to argue that there's nothing wrong with this. That in fact, this is exactly the issue that we've already seen multiple times before. It's really a product of inframarginality. Okay, and once let me go through the reasons, and I'll try to argue so I sort of understand that this feels bad. The idea is that once we are willing to understand the statistical subtleties of these types of inframarginal statistics, we're more willing to understand that, in fact, doing something else is discriminatory. This, in fact, is not evidence of discrimination in and of itself. Again, not to say the algorithm is not biased, the weaker claim, this does not suggest the algorithm is biased. Okay, now let's go through some of the misconceptions of false positive rates. So the first is the one that I just alluded to, that a higher false positive rate for some group implies discrimination. It applies taste-based discrimination. It suggests that we're applying a lower bar for one group relative to another. Now let's see what's going on in Broward County. So this is the real data in Broward County that we're estimating these risk distributions. And we see that the black group, like we saw in Raleigh, has this heavier tail than the white group. Now the algorithm, and again the 25% I'm just using for convenience here, it's approximately what's going on in Broward County, but this is just a number that I'm picking to make this example easier, is we're going to apply this threshold of rating high risk versus low risk. So we're converting these probabilistic estimates to binary classifications. Now let's try to understand what's going on. Again, that distribution conditional on features is given to us by nature. We can't alter that. We can ignore it, but we can't alter it. So what happens? So let's pick this apart even a little bit more. So this is just kind of a simpler example of this picture. We have our red group and we have our blue group. They have different means. The blue group is shifted to the left, red group is shifted to the right, and they have slightly different distributions. Now what is the false positive rate for the blue group? How do we compute this? We say among the people who did not reoffend, how many were detained? So we just can add up, an expectation at least, how many did not reoffend, how many of those people are on the right of the threshold. If we do that, we get a false positive rate of 25%. Let's do that for the red group. Now here, we're going to do the exact same calculation. It's 40%. What happens, I apply the exact same standard to both of these groups, but because the distributions vary, I have different false positive rates. Okay, now just highlighting this point, this is inframarginality. Because false positive rate is an inframarginal statistic, the same way that precision is an inframarginal statistic, it's a poor proxy for what's happening on the margin. It's a poor proxy for this common understanding of taste-based discrimination, meaning that we're holding individuals to the same standard. Can I postpone this for a minute before I get to the other?
I just didn't know what you're dividing.
Okay.
I literally just don't know what you're dividing in those two pictures.
So this is the definition of false positive rate among the people who did not reoffend.
So who are you adding?
So you have to add, so here you flip a coin for everybody. And you say, okay, some of these people, this is the probability of reoffending, I flip a coin, maybe they reoffended, maybe not. On average, 6 of these people reoffended. Of those, 2.5 were above. So it's a highly stylized example, but the point is once I give you the distribution and the cutoff, I can just deterministically compute the false positive rate. Okay, so now this, again, is inframarginality. False positive rate is analogous to precision. So now the second point The second, I'd say, misconception about false positive rates is that a higher false positive rate for a minority group is due to a lack of data. Now, there are two ways a lack of data could play into this, either a lack of training examples, or rows, or a lack of predictive features, which are columns. And these have different interpretations. So now, let's look at a lack of training data in terms of rows. Now, one thing I want to note here is that if this is, that once I give you my outcome variable, for example, recidivism, it doesn't matter, and I believe that estimate. If I believe that, and I have lots of data here, so I believe that I can accurately estimate that black defendants in Broward County have a higher recidivism rate than white defendants in Broward County. This is a relatively straightforward thing to estimate. I don't need a lot of data to do that. Once I believe that, that already pins down the means of these distributions. So more data isn't going to change those means. It might change subtly the shapes of these distributions, but the means are going to be quite different. In fact, in Broward County, we see that the means of black defendants is quite a bit higher than the means of white defendants. And again, no amount of data is going to get me out of that issue. So we know that these distributions are going to look quite different. And when these distributions look quite different, in particular when one distribution is shifted to the right of another distribution, that implies this type of behavior for false positive rates. It suggests significantly higher false positive rates for one group relative to the other. So collecting more rows is not in fact going to get us out of the problem. The other thing I'll say is that because of the nature of the criminal justice system, we in fact have much more data on minorities than on whites, even in absolute numbers. And so again, that's probably not what's happening in Broward County, but it's a useful thing to remember. I think this is a gut reaction that a lot of people have. This is because of a lack of data. A lack of data in practice is not the issue here. In theory, it's almost certainly not going to address these false positive rates. It's probably not an estimation problem. Now, what about enough predictors? So this is enough columns. So the idea here is that if I were to collect better information for black defendants and white defendants, I could drive down my false positive rate. It feels like we're doing so bad for black defendants, my false positive rate is so bad because I haven't bothered to collect good information. In fact, something quite paradoxical can happen in practice and in theory here, that if we collect new information, more predictive features, we can actually increase the false positive rate. So collecting more information, improving individual level estimates in one group can drive up my false positive rates. And this is likely to happen in many common scenarios. Okay, so let me explain this. And actually, let me flip this around so it's a little bit easier to understand. So I'm going to say that ignoring information can lower my false positive rates. This is the same statement, I'm just reversing it. So adding information can increase my false positive rates. Ignore information can lower my false positive rates. So why is that? Well, here I'm going to take my example distributions. And what am I going to do? I'm just going to squeeze it together for my red-black distribution. So that's ignoring information. I'm just going to throw out information for lots of individuals, and I'm going to make it look like everyone seems average for that group. Now, if I do that, what's going to happen is the average defendant is below the threshold. The average defendant is probably relatively low risk, and so all that's going to do is push everyone down here. Now let's see this play out. So as the risk scores get worse in the black group, and this is what we're trying to do, we're trying to lower the false positive rate for black defendants, then we lose the ability to distinguish between high risk and low risk defendants. And that's going to in turn lower my false positive rates. Let's see this. So what is the trick? It's the same trick that we used before. This is mechanically how we do it. In practice, you can do this just by throwing out information. We're just going to take the people on the edges, make them look average. What happens is that as I get worse and worse predictions, so here's my AUC. This is the red is the black group. Here's my AUC and my predictions. Over here is my using all the data. Here I'm artificially throwing away information about individuals. As I throw away information, I lower my false positive rate. Why is that? Because the distributions get closer and closer together. They get closer to the mean. And when I'm here, the AUC of 0.56, almost no predictive power, that's when I equalize my false positive rates. So the idea that the reason the false positive rates is higher in one group relative to the other is because I've done a poor job of predicting in that group relative to the other is wrong. In fact, adding, so I can equalize these things by throwing away information. The other way to say that is by adding information, by improving my risk scores, which we'd all agree is good. If I'm not using the individual level risk scores for someone, that means I'm detaining some people who I know are actually low risk, but I've decided to ignore that fact. But if I throw away information, I can start equalizing it. If I make better and better individual predictions, I might get higher error rates. So error rates are not a reflection of how well I fit my model. They're intimately related to the shape of these risk distributions. Now, the final one is that misconception of false positive rates is that they're a good proxy for group well-being. I'm using this word kind of generally, but let me show you an example of what I mean here. So here's what we had before. We had our two groups, 25% in the blue group false positive rate, the red group 40% false positive rate. And what am I going to do here? So this is corresponding to my black defendants and my white defendants. I might not like this, so I might say, well, let's try to lower my black false positive rate because it suggests that if these were equal, somehow the group would benefit. One way I can do this is I can just arrest lots of low-level college protesters. Why am I going to do that? Once I change my risk distribution, all of a sudden, if I look at my false positive rate, because these are low-level individuals, and I accurately know that they're low-level individuals, it only comes into the denominator. Because it comes into the denominator, it lowers my false positive rate. So all I'm doing is I'm going from something like this, where we might say, the groups are being treated, they experience some kind of harm by having differential false positive rates, to this, where now we say, okay, now the groups are equalized, and they're actually relatively low false positive rates. We're not raising anyone's false positive rate. They're all relatively low false positive rates. But I would argue that in the black group, they're worse off because now I've arrested lots of low-risk black college protesters. So it's a very hard argument to make that if you care about group well-being, all I have to do is change the distribution by acting in some, I would say, obviously perverse way, and now I can make it look as if the group is doing better.
Yes. You argue that once you have a calibrated score, you shouldn't stop there. We could also argue that once you have a difference in false positive rate, you shouldn't stop there, but you should perhaps also say, well, if I see a huge difference, I must sort of understand in my data what caused and justify that there's something.
Oh yeah, so I think I think that's exactly right. And I think of this similarly to how I think of the outcome test, in that it's a place to start out with. I said, well, maybe even a better analogy, I think of this in the same way I think of the statistic that many more black defendants in Broward County are detained relative to whites. It's something that you might think of as concerning. I mean, I'm concerned about that. And we have to understand, is that because of discrimination, or is it because something else? What I'm trying to argue here is that it's very hard to show that that is the product of discrimination. We have to understand what's driving it. In this case, we in fact do understand what's driving it. It was the first slide. Really, it's this. Once we understand these risk distributions, we have a much clearer understanding of what is driving these disparities. But we do have to go there. We can't simply say, oh, okay, in theory, these false positive rates don't need to be the same, so therefore I'm not going to do any investigation. My point only is that it's very weak evidence of discrimination, and in fact, the argument in this particular case, where we have done quite a bit of investigation, is that it doesn't look like it's the product of any any type of implicit or explicit bias. Okay, so now kind of one high-level point is I've been talking about false positive rates as a particular exemplar of error rate that's quite common. This is what I think a lot of us have these visceral reactions to, and also the notion that was used in ProPublica. This is just an example of anything that can be written down as a confusion table, a function of a confusion table. So all of these, so there are many, many definitions of fairness that have been proposed that many of them can be written as a function of this confusion table. So you think of something like precision parity, this is this outcome test type thing, statistical parity, so the equal number or equal proportion of individuals in different groups are detained at the same rate, or recall parity, or equalized odds. All of these things are functions of the confusion matrix. And all of them suffer from the exact same problem. They all suffer from inframarginality. they're all based on averaging over regions of the risk distribution that are far from the threshold, and so give us relatively little diagnostic or normative insight into whether or not discrimination is present. So now I want to return to this question of are the data biased in some way, and also return to this anti-classification notion of discrimination. So this idea of are data biased, I would say there are at least two ways of formalizing this idea. The first is, are the predictors biased? And the second is, are the labels biased? Now, I'll argue that the first one is easily addressed statistically. The second one is essentially impossible to address, but it's also largely outside of the realm of computer science and statistics. It's a problem that I actually have been grappling with recently. It's very, very hard to deal with, but these are two different notions of bias which are qualitatively different in their implications. So let's look at the first, bias predictors. Are the features differentially predicted? So in Broward County, women are less likely to reoffend than men of the same age with similar criminal histories. That's just a fact about Broward County. It's perhaps not particularly surprising, but it's what we in particular see in Broward County. So what does this mean? That a gender-neutral model, which is used in Broward County, ends up with a plot like this. So I'm showing you here the recidivism rate as a function of the risk score that you get out of the algorithm. And what happens is that if any one of these risk scores, if I look at something like 7, I see that women recidivate at a much lower rate than men. And if I actually were to draw a threshold here, which is what is done in Broward County, what I'm doing is I'm exacting a 2-point penalty for women relative to men. I'm saying that I'm willing to detain relatively low risk women because I fit a model in a way that overestimated the risk of one group relative to the other. Okay? And this is the problem with anti-classification. So if I want a gender-neutral model, I'm stuck. I'm stuck with this picture. And if I apply my single threshold, all I'm doing is I'm detaining women who I actually know are low risk relative to the same men at that threshold. Now this is a pretty easy fix statistically. You just fit one model for men and another for women. Or another way of thinking about this is you use gender in the model and you throw in interactions. These are statistically quite easy. And in fact, Wisconsin does this, that it uses gender-specific models to make sure that we don't have this type of discriminatory behavior.
And so is this equivalent to saying that the COMPAS risk scores are not correct in terms of y given x if we reinterpreted 1 through whatever as like some measure of risk?
Yeah, so it is, and I would say just to give Equivant, the company that made COMPAS, a little bit of relief here, is that they offer gender-specific models. Broward County decided not to use it. And I would say this stems from this idea that anti-classification is a strong legal concept of discrimination. And that is not correct. So this is, I would say, an incorrect understanding of the law. In Wisconsin, this has been litigated. It went to the state Supreme Court. This was raised under due process, not equal protection, so the legal standing is a little bit different. But the court ruled that, in fact, a gender-specific tool satisfied a compelling government interest to make sure that individuals were treated fairly. So the idea of anti-classification, you should think of it as something you might raise your eyebrow at. If I say, okay, you're using gender in your model, it makes me suspicious. It's true. If you say that you're using gender, if you're saying you're using race in your model, I'm naturally going to be suspicious. But now you have an opportunity to say whether or not that's legitimate. And this is exactly what's going on. And so this is what we're advocating for in California. There's a bill coming up for a vote in California, and we're working to try to modify that bill to allow the use of gender in risk scores. New Jersey has recently passed a bill that allows the use of gender in risk scores. Wisconsin is already using these things. And so I would say this anti-classification idea stems from both a statistical misunderstanding and also a legal misunderstanding of fairness. So maybe I can postpone just to wrap up, and then I'll take questions. So now we switch this much harder question of bias labels. Now, bias labels, what does this mean here? That the entire time I've assumed that we have this perfect counterfactual estimate of y, of this thing y that I care about, so of assault. In reality, what do we have? We have arrests or convictions. We don't have who committed a crime or who would have committed a crime. Now, in some cases, we might think that drug crimes are a relatively poor proxy for, or drug arrests are a relatively poor proxy for the actual criminal act in and of itself. So as one data point, we know that by survey data, that use of minor drugs is relatively comparable among whites and blacks, but arrests and convictions are much higher for blacks relative to whites, which suggests that this is an inappropriate measure for assessing the underlying behavior. For some outcomes like violent crime, we are much less prone to measurement error. That it's believed that when violent crime occurs, it's more likely to be, or it's not differentially reported. In others, for example, failure to appear, so flight risk is even better reported. We don't have the counterfactual estimate, but we do have an estimate of whether or not someone actually showed up in court. And so I think this is a spectrum of what happens, this type of bias problem, but I would say that it is a very serious problem, and I would argue that we don't have good methods for combating this problem. At the same time, we have to make decisions. And so this isn't an algorithmic problem, it's just a problem in decision making, and we have to figure out what to do, but it's not inherently something that is, it's largely that is outside the scope of what I've been talking about. So now, just wrapping up, let me just try to summarize. So the first is that mathematical definitions don't apply any notion of equity, and the vast majority of mathematical definitions that have been recently proposed don't map onto either established legal or social understandings of fairness. And this has three important consequences. The first is that nearly all of these mathematical measures of fairness are poor proxies for detecting discrimination. So if I tell you that false positive rate is higher for one group or the other, I can tell you very, very little about whether or not there was discrimination. The second is that if you try to equalize these types of measures, that itself will almost always lead to discriminatory behavior. I could try to equalize these measures by applying different standards. I could try to equalize these measures by throwing away information. I could equalize these measures by changing my population. Any of these types of fixes to this are going to result in discriminatory behavior. Now, the final, and I haven't really talked about this, but it's a corollary of these results, is that it's pretty common to talk about trade-offs between different measures. For example, there's a trade-off between precision and recall, or any of these other types of fairness, or precision parity and recall parity, or a trade-off between false positive rate parity and statistical parity. In fact, I would say many of these are illusory. Why is that? Because as point 1 and 2 are showing, in fact, you don't care about most of these measures. And so once you are willing to accept that neither they tell you much about underlying discrimination, nor should they be equalized, the fact that they're not equal in practice tells you relatively little. And so the idea that they're trade-offs and that we're sacrificing false positive rates in order to get something else, in fact, we didn't care about false positive rates. It was a poor proxy for the thing that we actually cared about, which was some sort of version of equal treatment. Now, that was the kind of the contrarian kind of nihilist view of algorithmic fairness. I'd say, in fact, things are looking pretty good in many of these domains that I've talked about. In fact, practitioners have largely solved many of these problems that we as a community have been struggling with for the last couple of years, namely applying a threshold rule. So fitting the best scores that you can fit given the available data, drawing a threshold, making your actions conditional on the side of the threshold that one falls. Now, this isn't perfect, but it's actually pretty close to what one wants to do. There are a couple important assumptions here that Jamie and Rachel are going to start talking about. Here it assumes that there's lots of data. In the criminal justice setting, usually that's satisfied. And it assumes that we have accurate outcome measures. Usually we don't have that, but in fact we'll never have that, but we still have to make decisions. Algorithmic or otherwise, we have to make these decisions, and so we have to think about what is our best proxy for making this. So now, just a few caveats to wrap up. We focus on the immediate costs and benefits of decisions, so the immediate cost of detention versus the benefits of preventing recidivism. There are long-term equilibrium effects that might justify multiple thresholds. I think that's an important argument to understand. I think it's also not one that should just simply be thrown out there as saying we care about equilibrium effects, so therefore we'll have different thresholds. I think one has to make a very rigorous argument about why it is that different thresholds in a particular situation will give rise to the equilibrium effects that we ultimately want. So I think it's very hard to make that, but it is something that I want to throw out there as what we would like to think about as a community. Also, I've largely assumed that costs are constant across individuals. So if I detain someone who's white, that's roughly the same thing as detaining someone who's black. Financial costs, social costs, I've assumed that these are all roughly the same. They're not actually all the same if we break down to different subgroups. I would say on race, it's hard to make an argument that they're different, but here's one case where it is. If I detain a single parent, I would argue that that's more costly than detaining someone without children. So given these types of differential costs, we might want to set different standards. And now some decisions that have come up already, like college decisions, really apply to groups rather than individuals. So said another way, they're externalities. In many situations, the externalities are second order compared to the individual decision. But in some situations, the externalities themselves are actually the dominant effect. And so we have to worry about that. So certainly I don't want to give the impression that this is a kind of complete story of fairness, even under the assumptions that I laid out at the beginning. But I would argue that this is a fairly general description of fairness in many of the domains that we care about. Now, the last point here is that algorithms are not policy. And arguably, this is the most important point of the talk, is that algorithms, statistical algorithms, are very good at synthesizing information. That doesn't get us out of the problem of setting equitable policy. In the bail case, what this might mean is that we might eliminate money bail. It might mean that we consider non-custodial detention or non-custodial interventions. It means that we can take on all sorts of different actions, but what we can't do is ignore the risk. The algorithm is giving us a risk. We have to decide what to do with that risk. To give you another example, an algorithm might accurately tell me that if I do nothing else, this person is likely not going to show up at their court date. If I dig deeper, I mean, that might be a perfectly true statement. If I look deeper, I might say, well, that's because they don't have access to transportation. So the intervention isn't detain them. The intervention is give them transportation, give them subway fare. Now, that doesn't mean let's change my risk distribution. That doesn't mean let's forget about the fact that this person is high risk. What it means is that the risk does not actually map on to policy. We have to make that choice. And my sense is this kind of slippage between policy and the algorithm is in fact driving a lot of the appeal for trying to equalize false positive rates, when really these are two separate questions. One is a statistical problem, and one is a policy problem. So I've covered a lot of material. If you're interested in more of these, I'll point you to two papers. I've talked about quite a bit of things, but these will give you some of the pointers. This first one talks about discrimination in human decision. In particular, it talks about this problem of inframarginality in quite a bit of detail. The second one talks about algorithmic decision making and brings up this notion of inframarginality and why statistics like false positive rates are generally inappropriate for diagnosing or acting on algorithmic decision making. If you're generally interested in this area of computation plus policy, check out the Stanford Computational Policy Lab. This is a new initiative that we recently started in the last few months, where we're using these ideas from statistics, from machine learning, to interface with a lot of policy problems. Let me give you two quick examples. The first is the Open Policing Project. So this is where we've developed a lot of our intuition about bias in human decision making, particularly in the context of policing. We've released all of our code and data for over 100 million traffic stops across the United States. We're going to do a large data dump again this summer. This is a multi-year project that we've kind of cleaned all the data and made it fully transparent and available for individuals to play with. The second, as I had mentioned earlier, is that we're actively engaged in bail reform in California. We think this is the use of algorithms, I think, is a positive step forward in criminal justice, but I think this has to be done very carefully. And we offer several recommendations for improving the upcoming legislation in California. So please take a look at some of that work as well. So I'll end it with that. Thank you. So I'm basically out of time, but maybe I will take just a couple questions. If people also want to step out, feel free to. We'll start at 4 o'clock for the second half. So please either feel free to step out or ask questions. Yeah, thanks.
So I really like this. First of all, thank you. So I'm having some trouble reconciling two things, so on one hand you argued against calibration, which I kind of agree with you with, right, the issue of destroying information. But then, and I guess this maybe what some of the questions we're getting at, earlier on you said that as researchers we often don't really have access to the features that decisions were made on, right?
Yep.
And so for any calibrated risk scores, it's conceivable that that was exactly the information that was available, in which case they're actually doing exactly what you're suggesting we should do with them.
Yeah.
So how could we ever detect for any calibrated risk scores that they're not doing the right thing?
Yeah, so you can't. In theory, you can't do it from the outside. And so this is why a lot of our work is in partnership with these organizations. And one of the things that we're advocating for in California is a broad data policy that gives researchers access to sensitive information while also preserving the privacy rights of defendants. So I think, theoretically you can't do it. If I just give you a risk score, you can't tell me if I did something that was good or bad. And that's just what we have to live with. But if we want to move policy forward, I think we have to accept the fact that that's a very poor proxy for what we ultimately care about and work to build these partnerships with the decision makers themselves. Yeah, please.
So you talked about how sometimes this anti-classification doesn't make sense. Are there situations where it does make sense to explicitly ignore things that you know?
So this is a complicated question. So the first thing is, for race, we've never seen evidence that race is adding predictive power to tools. At the same time, for these types of pretrial tools, at the same time, we don't think that something like housing stability and socioeconomics is actually adding a lot to, for example, violent recidivism. And so what we advocate for in California is that those, because they add to the perception of bias, they not be included. In theory, in the limit, you're losing a little bit of performance if you don't do that. But I think there's a trade-off between the appearance of fairness and the actual best statistical tool that you can get. So you're always losing a little bit. I would say in certain situations, that's okay. The other situation where a little bit of information loss is okay is that in almost all of these pretrial algorithms, they're really just checklists. There are 6, 7 features. They're given to defendants. They're given to the judge. And that is a coarsened version of the full random forest or whatever you're going to fit on the data. And we're losing some accuracy when we do that. But again, we establish some of these due process guarantees. So it's tricky. I would take the middle road and say, in practice, yes, I'm happy to throw away certain amounts of information. In theory, there's this trade-off. Yes?
Also, kind of building on his question, what do you think about questions that kind of proxy race as well, right? So I think specifically on the Compass questionnaire, they ask a lot of questions about like your zip code, about like how many family members you've handled in the criminal justice system, and so forth. And those are often very effective proxies for identifying a person as African American. Like, what do you think about those kinds of stuff?
So I would say that idea is essentially not represented it doesn't appear in this framing of the problem because everything is correlated with race. So the idea that some things are taboo and some things aren't is a very, very hard normative argument to make. Really, we're saying use all of the information, including something like race, including something like gender, which are sensitive on their own. They're not simply proxies for sensitive features. They are the sensitive features themselves. And I'm saying that even those should be used in the algorithm in theory to prevent the types of discrimination that we're finding evidence of. So once you accept that reality, the idea that we're going to ignore information that's highly predictive of sensitive features is not one that comes up. So I would say this is the misunderstanding of anti-classification as an ideal in and of itself, rather than something that might make one wonder whether or not you're doing the accurate thing.
Yeah, I'd like to make sure I'm not characterizing what you say. The dogma of big data was we got a model with lots of information, it's very accurate, better than anything we can judge. So now trust that risk and apply a threshold to that. That's what we've been doing for 5 years. And then people have been saying, well, there are actually consequences, we need to be careful for fairness. And you're saying, no, all these tests showing concern are wrong, and the end solution is only to go back to use the best model, use the data. And I'm not arguing it's necessarily a bad thing to do.
Yeah. So it's controversial. So I'll admit it. It's controversial, and the implication is the vast majority of papers that have been written in this topic are problematic. They're problematic legally. They're problematic normatively. They are they are out of line with well-established social principles of of fairness. And in fact, they're out of line with what practitioners are currently doing. I think that that is an implication.
Okay, okay. So that's what you said.
Yes. You didn't misunderstand. And I'm happy to, respond to pushback on that. It's a strong statement.
I feel like the problems you pointed out with false positive was contextual, but somehow like the counterbalance, because you're showing that it's not discriminatory because equal threshold would also produce this false positive. But that means you're assuming equal threshold is a good way of ensuring fairness. But maybe it's not.
Mm-hmm. So this, I would say, of course, one could argue that it's not. I would say that the standard economic and legal view of this question, I would say one that in fact resonates with many of us, if we forget everything we've heard about in the last 2 years, is that equally risky people should be treated equally. That if I say that you have a 20% chance of recidivating, I don't need to ask, are you white or are you black? I would say, if I believe that this is my standard for detention, that is my standard for detention. I don't say that I'm going to detain a white individual at a 20% chance, but a black individual at a 50% chance.
But that assumes trust on the risk score calculation. That assumes trust on likelihood number calculation, but which people don't trust.
Sure. So that was one of my big assumptions at the beginning, that you have to have an accurate measure of the outcome and you have to have an accurate measure of the risk. In many of the cases that we consider, we have the latter. We have lots of data, so we have that thing. Now, what my pushback is, even if these are violated, it's a hard argument to make. This is violated, so therefore I can do whatever I want to do. And what I want to do is equalize false positive rates. That's a very hard normative argument to make. It's saying that, yeah, I should worry a little bit about my risk scores, but saying just because I don't perfectly agree with the assumptions of the framing, I can do whatever I want is hard. And what I've tried to persuade you of is that in almost no circumstance should you try to equalize false positive rate, because in fact it doesn't capture what many people think it captures. It's an informational statistic that's highly dependent on the lower tail of the distribution, and that lower tail of the distribution is difficult to say much about normally.
And we do maybe want to, we probably want to wrap up and go to break in a second,
Yeah.
but I do want to say that, I agree with Sharad that, there are issues that come from a lot of these constraints, but also that, it is also a somewhat controversial perspective to say that we should be looking at risk and basically equalizing the risk the risk threshold at which we make a decision for different populations. That's not a generally agreed upon concept. Universal.
I would say so that's
universal.
So that's maybe I'll say
being
one.
asked here sort of address reasons of why we may not always want to.
And I'll add that my point here is that it's true it's not universal, but the odd ones out are computer scientists. So mostly legal experts, practitioners, policymakers, economists agree that this is very close to an appropriate notion of fairness. And part of this, and this is the controversy here, is that as a community, we have strayed from this large body of literature. And what I'm arguing for is that it's a dangerous place to be. That once we look at these types of measures that in fact don't map onto established notions of fairness, and I would argue that in fact many of us in this room in fact agree with, all sorts of bad things can happen. That if we try to achieve these definitions, in fact we're very likely going to be discriminating. It's not simply a possibility, but we're almost certainly going to be discriminating in a way that's both illegal and at odds with social norms.
I don't think anyone ever argued to equalize false positive at all costs, in any situation. I think most of the conversation happening in the last 2 years were there is something there we should figure out. And the second thing I think is many of the most important papers show that sometimes there's a bias in the way you measure, and you want to have tools to be wary of that. And your risk score clearly was the best given the data, but there's a lot of things in the data you should criticize, you should understand better. And it's partly for computer scientists to help with that. So I think we have to move on beyond those. But I like your view.
So I think that's
I really appreciate it.
I think that's true. I would say that the most highly cited papers in this area are equalizing these types of measures.
No, they are not advocating to equalize. They are giving examples where perhaps that's interesting.
And that's,
Perhaps we can fight about the scholar citation counts during the coffee break. All right. And I think in the interest of time, we'll restart at say 4:10.